minus 15 seconds. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0, and liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
Program complete.
So a lot of people wonder why Curiosity doesn't have solar panels like the Mars exploration rovers, Spirit and Opportunity. The Mars exploration rovers often found themselves short on power as dust settled on their solar panels. This was especially a problem in the short days of winter. Curiosity is 2 times bigger, 5 times heavier, and has 15 times the weight of scientific equipment relative to Spirit and Opportunity. Like those rovers, Curiosity surveys the landscape and examines rocks up close. Curiosity's scientific mission involves driving around its landing site, perhaps up to 15 or 20 miles, collecting samples of rocks and soils with a big jackhammer drill located on the end of a 6-foot robotic arm. Those samples are delivered to the rover and analyzed with some very sophisticated and power-hungry analytical laboratory instruments. And that's where the MMRTG comes in, the multi-mission radioisotope thermoelectric generator. On this half-scale model of the generator, you can see what's inside. The generator contains a specially produced form of plutonium dioxide. The natural decay of this radioisotope gives off heat, which these thermocouples can turn into electricity.
Over here, we have our crew stage. The crew stage is comprised of a solar array, several guidance sensors, and a propellant system that basically gets the MSL spacecraft from Earth to Mars. Once we get to Mars, the vehicle will have served its purpose and we jettison it and it burns up in the atmosphere before we actually make first contact with the atmosphere itself. The back shell is the vehicle over here in white, which provides an interface to a large deceleration parachute. And over here is the heat shield, and the heat shield has the protective insulative tiles that keep Curiosity safe as all the heat is generated as we actually wake our way through the Martian atmosphere. Behind me is the descent stage. The descent stage is the jetpack that safely gets Curiosity down to the surface of Mars. Unlike Pathfinder and the twin rovers Spirit and Opportunity, which utilized airbags to make it down to the surface, Curiosity relies on the descent stage and this jetpack to actually make it down to the surface. So here's the star of the show, the Curiosity rover. Here Curiosity looks the same way that she'll look when she makes it to the surface of Mars and deploys all of her mechanisms.
Not only have we driven the rover, we've moved its arm, put it all through its paces, but it's been in a thermal vacuum chamber and kept very cold. Parts of it have been on through in a centrifuge. We've done drop tests, pull tests, drive tests, load tests, stress tests. Just an amazing amount of testing this vehicle has gone through. We've done shorting tests. We've taken the vehicle and shorted electronics. We've looked to see that the radios all work together and that the rover doesn't interact with itself in bad ways. We've tried every way of operating the vehicle using the software, literally thousands and thousands of hours of software testing.
We have 4 wonderful landing sites, all very different in character. And the real challenge for us as scientists is to come to a consensus on which one of those sites offers the best chance of fulfilling the goals of the mission. There's a place on Mars called Marth Vallis, which has the brightest mineral signature of clay minerals on Mars. And these clay minerals are known to form in the presence of water and neutral pH water, not acidic, not too basic, just the kind of water that would be friendly to life. Then you have terrestrial geologists who say that the rock record should be the thing that we follow, the landforms that look like they were carved by rivers or floods. So you have sites like Holden Crater, which is a big impact crater many miles across with a river coming into it, perhaps forming a lake multiple times and flooding the crater, leaving a geologic record that we can study with Curiosity. Just upstream a little bit from Holden Crater, there's a place called Eberswald Crater. That same river system in Eberswald has left evidence of a delta. Just like the Mississippi River Delta, these things form when muddy, silty water deposits its silt, its mud, into a formation, into a standing body of water like a lake. So you have people that study deltas on Earth who think that's the place Curiosity should go. The final site is the best place on Mars if you want to just study layered materials. So why do we like layered materials? Because just like this outcrop behind me, they give a record of time, of how things change over time. By studying different layers, you can rebuild the geologic history of Mars. So there's a place called Gale Crater, which has a 3-mile stack of layered rocks.
You can see our landing ellipse down at the bottom there, which is the white circle, and in the middle of Gale Crater is this mountain of rock that is 5 kilometers high, made layer by layer by layer. But the layers at the bottom are the ones that we're most interested in because we think that those were deposited in an aqueous environment, which is very important for understanding habitability. What you can see here now is that we're about to land very close to the center of the landing ellipse, and we have a couple of different routes that we can take. The scientists on the team prefer the one on the right, and so what we would do is drive along it. And now you can see at the base of this mountain where these lower layers are. And the layers are important because they allow us to sort of read a geological book. You start at the bottom of the mountain, and those are the oldest layers. And then the layers that occur up near the top, those are the youngest parts, the youngest chapters in the book. We will drive along up to this outcrop that we call the fence. And when we get there, we're going to study it. It's a really attractive spot for us because it contains the kind of minerals that formed in water. And then when we're done with that, we're going to go beyond and we're going to enter a canyon. And this kind of terrain around here reminds us a lot of Sedona, Arizona. And all the rocks around here are formed in aqueous environments. And so there's a lot of rock, hundreds of meters of it, layer after layer that we can study to tell us about the history of Mars at Gale Crater. Now we cross a boundary and we go into a very different type of rock. You can see how it weathers very differently. It's really rugged. So at that point in the mission, we'll be beyond our initial mission of 2 Earth years. This will take us into many years afterwards of exploration as we drive around this very rugged terrain. If we make it, we'll be able to look back over the area that we have previously studied, back down in towards the bottom of Gale Crater, back towards our landing ellipse.
It makes us a little nervous sometimes. I mean, you worry about the environment. It's on a forklift. It gets put on the back of a flatbed truck and then run down the highway to March Air Force Base from JPL. It's going to be a big push, but That's kind of how the end game goes. We try to get things ready, and every last thing has to be done and done right. It takes a lot of time and a lot of effort to do it.
We require our system to be able to be robust, to survive a number of different kinds of faults, both internal faults, things breaking on the spacecraft, or loss of sun data coming into the sun sensor, a variety of unfortunate circumstances we try to make our design robust to.
It's almost hard to imagine how complex it is. And in fact, if you get close up to the vehicle, you can see the richness of detail. And in fact, this vehicle almost has fractal-like complexity. So hopefully we'll take a big breath in mid-November before we launch and be able to relax and let this vehicle off the ground and finally say goodbye. I think she's ready to go.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0, and liftoff of the Atlas V.
Five seconds. Spacecraft set. Achieved our targeted roll rate. We have spacecraft separation. And confirmation from our video system. And the vehicle has despun.